Okay, hi everyone, welcome back to this live stream for Windows Server 2003. So we'll start on chapter 7, managing remote access services. Microsoft exam objectives covered in this chapter. Configure routing and remote um, access user authentication. Configure remote access authentication protocols. Configure Internet Authentication Service IAS to provide authentication for routing and remote access clients. Configure routing and remote access policies to permit or deny access. Manage DHCP. Manage DHCP relay agent. Troubleshoot DHCP. Verify that the DHCP relay agent is working correctly. Manage remote access, manage devices and ports, manage routing and remote access clients. Until now, we focused primarily on communications between computers on the same physical network. This works fine when every machine is located within a single building or campus, but many users need to access the network from remote locations, and standard LAN technology won't provide them with the connections they need. Instead, they must use special dial-up or virtual connections that provide access to the network over telephone lines or through the internet. Dial-up networking on the client side and remote access services on the server side provide another way, in addition to LANs, to carry network protocols you're already using. In the case of routing and remote access services, or RAS, some security services necessary to efficiently provide remote access are also provided. For example, you'll probably want to have effectively provide remote access also provided. So, for example, you'll probably want to have the ability to restrict user dial-up access by group membership, time of day, or other factors, and you'll need a way to specify the various callback, authentication, and encryption options that the protocol support. You'll learn about both dial-up and remote access in this chapter. You'll also learn about virtual private networks, VPNs, which provide remote access to private networks across public connections. Clients can dial into an ISP to an ISP and connect to your private network across the internet. The main benefit of this is reduced cost because long distance calls are unnecessary. VPNs are becoming more popular due to the increased popularity of high-speed internet connections such as cable and digital subscriber line DSL. Many of the features included in Windows Server 2003 are simply carried over from Windows 2000 with a few minor additions. This is the case with the routing and remote access console, or RAS itself actually dates back to the Windows NT4 option, and Windows 2000 Windows 2007 sported a completely revised version. Windows 2003 adds a few new features to RAS, but it remains mostly intact from the previous generation of Windows. Before you can get into the details of what these features do and how you configure them to provide remote access for your network, you need to understand some of the terms and concepts specific to RAS remote access. That's where you'll begin in this chapter, and then you'll move on to reviewing the features and configuration settings that you need to understand to meet exam objectives. Overview of dial-up networking, DUN. LANs provide relatively high-speed connectivity to attached machines, but where does that leave us who work from home, travel, or need to access data on a remote computer? Until wireless access is available worldwide, we're stuck with the familiar concept of dial-up networking with one computer, the client, dialing a remote server. Once the connection is established, a variety of protocols and services make it possible for us to view web pages, transfer files and emails, and do pretty much anything we could do with a hardwired LAN connection, albeit at reduced speed. In the following sections, you'll learn more about what dial-up networking does and how it works by examining the specific technologies and protocols associated with remote access. What DUN does. From reading chapter 1, you already understand that Windows Server 2003 network protocols are actually implemented as drivers. These drivers normally work with hardware network interfaces to get data from point A to point B. What about dial-up connections? Think back to the OSI model. Each layer has a function, and each layer serves as an intermediary between the layer above it and the one below. By substituting one driver for another at some level in the stack, you can dramatically change how things work. That's exactly what Windows Server 2003's DUN subsystem does. It makes the dial-up connection appear to be just another network adapter. The DUN driver takes care of the work by making a slow asynchronous modem appear to work just like a fast LAN interface. Applications and services that use TCP/IP on your DUN connection never know the difference. In fact, you can configure Windows Server 2003 to use your primary connection first and then pass traffic over a secondary connection like a dial-up link if the primary connection is down. On the server side, DUN allows you to host one or more network users who dial into your Windows Server 2003 machine. Windows 2000 Professional and XP Professional allow one dial-up user. Windows Server 2003 allows up to 255, although by the time you allow that many connections, you'll probably be overloading your server. Depending on how you configure the DUN server, users who dial in can either see only resources on the server or see the whole network. You also get to control who can log on and when they log on and when they can do and what they can do once they've logged on. As far as Windows Server 2003 is concerned, a user connected via DUN is no different from one using resources over your LAN, so all the access controls and permissions you apply remain in force for DUN users. How DUN works. There are a lot of pieces required to successfully complete a dial-up call from your computer to a server at another physical location. Understanding what these pieces are, how they work, and what they do for you is key. In the following sections, we'll look at the DUN infrastructure, how the point-to-point protocol PPP helps in this connection, the relationship between PPP and the network protocols, and how multi-link can be used to increase the speed and efficiency of your remote connections. The DUN infrastructure. Let's start with a look at the physical layer that underlies voice and data calls. Most of the following material will be familiar to anyone who has ever used a modem, but you should still understand the details that you might not have thought of before. POTS. POTS stands for plain old telephone service. In the early days of dial-up networking, phone lines were used to connect. You were lucky to get 4,800 BPS. At the time, the prevalent modem speed was 300 BPS. Today, modems offer a theoretical maximum speed of 56 kbps. In practice, many users routinely get connections at 51 or 52 kbps. The word modem is actually an acronym for modulator demodulator. The original Bell system modems took digital data and modulated it into screechy analog audio tones suitable for use on regular phone lines. Because phone lines are purposely designed to pass only the low end of the audible frequency range that most can hear, the amount of data was limited. However, in the early 1990s, some engineers discovered that you could communicate much faster if the path between the sender and receiver was all digital, because an all digital path doesn't have any analog components that induces signal loss. So it preserves the original signal quality faithfully, which in turn makes it possible to put more information into the original signal. As it happens, phone companies nationwide were in the process of making or had just completed major upgrades to replace their analog equipment with newer, better digital equivalents. These upgrades made it possible for people in most areas to get almost 56 kbps speeds without changing any of the wiring in their homes or offices. The connection between the house and the phone office was still analog, but the connections between the phone offices were digital, ensuring high quality connections. ISDN. In the mid 1970s, Integrated Services Digital Network was designed. At the time, no one had any idea you'd be able to get 56 kbps speeds out of an ordinary phone line. ISDN's speeds of up to 128 kbps over a single pair of copper wires seemed pretty revolutionary. In addition, ISDN had features like call forwarding, caller ID, and multiple directory numbers, so you could have more than one number, perhaps with different ringing patterns associated with a single line. Unfortunately, ISDN requires an all digital single path. It also requires special equipment on both ends of the connection. The phone companies were slow to promote ISDN as a faster alternative to regular dial-up service, so customers avoided it. ISDN still has some advantages, though, because it's all digital. Call setup times are much shorter than they are for analog modems. It only takes about half a second to establish a new ISDN call. Most ISDN adapters and ISDN capable routers can seamlessly stitch together multiple ISDN channels to deliver bandwidth in 64 kbps increments. Because you can use ISDN lines for regular analog voice, data, and fax traffic, you can make a single ISDN act like two voice lines. A single 128 kbps data line or 64 kbps data line plus a voice line. Other connection methods, POTS and ISDN, aren't available everywhere. For example, suppose your company has a Windows Server 2003 network and has sites on land as well as at sea. The computers at sea must communicate with land-based offices via a satellite-based connection. In theory, it's a dial-up connection like any other, it actually but in actuality it uses a packet-based protocol called X.25. X.25 can be used to substitute for a regular dial-up connection in Windows Server 2003, assuming you have the right drivers and hardware. Any other on-demand connection that's established using the point-to-point protocol PPP can be thought of as a dial-up connection. Windows Server 2003 doesn't make any distinction between POTS, ISDN, or other dial-ups. They're all treated identically. Connecting with PPP, the point-to-point protocol enables any two devices to establish a TCP/IP connection over a serial link. That normally means a dial-up modem connection, but it could just as easily be a direct serial cable connection, an infrared connection, or any other type of serial connection. Whether one machine dials another, the machine that initiates the connection is referred to as a client, and the machine that receives the call is a server, even though the PPP itself makes no such distinction. The PPP negotiation involves three phases that are required to establish a remote access connection. The three phases invoke one or more protocols, as you can see in figure 7.1. There are actually at least 6 distinct protocols that run on top of PPP. Understanding what they do helps make the actual PPP negotiation process clearer. These protocols include the following: the Link Control Protocol, LCP. The Link Control Protocol handles the details of establishing the lowest level PPP link. In that regard, you can think of it almost as if it were part of the physical layer. When one PPP device calls another, they use LCP to agree that they want to establish a PPP connection. The Challenge Handshake Authentication Protocol, Challenge Handshake Authentication Protocol, as well as MS-CHAP, PAP, and SPAP, which will be covered in the next chapter, allows the client to authenticate itself to the server. This authentication functions much like a normal network logon. Once the client presents its logon credentials, the server can figure out what access to grant. The Callback Control Protocol, CBCP. The Callback Control Protocol, CBCP, is used to negotiate whether a callback is required, whether it's permitted, and when it happens. Once the client has authenticated itself, the server can decide whether it should hang up and call the client back. The client can also request a callback at a number it provides, although this isn't as secure as having the server place a call to a predetermined number. It provides some additional flexibility. If a callback occurs, the connection is re-established and re-authenticated, but the CBCP stage is skipped. The Compression Control Protocol, CCP. The Compression Control Protocol allows the two sides of the connection to determine what kind of compression, if any, they want to use on the network data. Because PPP traffic actually consists of wrapped up IP datagrams, and because IP datagram headers tend to be fairly compressible, negotiating effective compression can significantly improve PPP throughput. The IP Control Protocol, IPCP. At this point in the call, the two sides have agreed to authentication, compression, and a callback. They haven't yet agreed on what IP parameters to use for the connection. These parameters, which include the maximum packet size to be sent over the link, the maximum transmission unit MTU, have a great impact on the overall link performance. So the client and server use the IP Control Protocol to negotiate them based on the traffic they expect to be passed. The Internet Protocol, IP. Once the IPCP negotiation has been completed, each end has complete knowledge of how to communicate with its peers. That knowledge allows the two sides to begin exchanging IP datagrams over the link just as they would over a standard LAN connection. Figure 7.1 shows how these protocols work together to lead up to establishing the link. Remember, this diagram because you'll see it again when you start reading about PPTP. Now you can see what happens after the link is established and traffic begins flowing. The relationship between PPP and network protocols. Normally, when you hear about network communication, you hear about using TCP/IP, NetBEUI, AppleTalk, or IPX, SPX on a hardwired LAN. How did these protocols fit in with PPP? In the case of TCP/IP, that's an easy question to answer. The client routes all or some of its outgoing TCP traffic to its PPP peer, which can then inspect the IP datagrams it gets back from the PPP stack to analyze and route them properly. Windows Server 2003 doesn't just support TCP/IP, so consider what has to happen when a client using NWLink needs to connect over the dial-up networking. After the LCP negotiation completes, the server will know which protocols the client wishes to use. If the server doesn't want to use one or more of these protocols, it can drop the call and calls the client to warn its user that what Windows Server 2003 does. After the other PPP setup steps complete, the client and server can wrap other types of network traffic inside an IP datagram. This process, called encapsulation, allows the client to take a packet with some kind of private content, wrap it inside an IP datagram, and send it to the server. The server in turn processes the IP datagram, routing real datagrams normally and handling any encapsulated packets with the appropriate protocol. At that point, the client can communicate with the server without knowing that its non-TCP IP packets are being encapsulated in any way. That detail is hidden deep in the layers of the OSI model, understanding the benefits of multi-link. Many parts of the world don't have high-speed broadband access yet. In fact, many places don't have ISDN or even phone lines that support 56K modems. The multi-link extensions to the point-to-point protocol provide a way to take several independent PPP connections and make them look like one line so that they act as a single connection. For example, if you use two phone lines and modems to place two-line multi-link call to your ISP, instead of getting the usual 48 kbps connection, you would end up with an apparent bandwidth of 96 kbps. The multi-link PPP software on your Windows Server 2003 machine and on the ISP router takes care of stringing all of the packets together to make this process seamless. Windows Server 2003's RRAS service supports multi-link PP for inbound and outbound calls. The primary drawback of multi-link calls is that they take up more than one phone line apiece. Overview of virtual private networks. Private networks offer superior security. You own the wires, you have control over what they're used for, who can use them, and what kind of data passes over them. However, they're not very flexible because you would need to configure and manage costly leased lines between remote locations. To make things worse, most private networks face a dilemma. Implementing enough capacity to handle peak loads almost guarantees that much of the capacity will sit idly much of the time, even though it still has to be paid for. One way to work around this problem is to maintain private dial-up services so that a field rep in Chicago, for example, can dial the home office in Boston. Dial-ups are expensive and they have some excess capacity problem that truly private networks do. As an added detriment. Users who need to dial up in from long distances have to pay long distance charges unless they use toll-free numbers, in which case the remote access costs go up dramatically. Virtual private networks offer a solution. You get the security of a true private network with the flexibility, ubiquity, and low cost of the internet. In the following sections, we'll look at VPNs, what they're used for, how they work with Windows Server 2003, and how they work in general. So I'm going to leave it here today for this live stream. Thanks for listening and have a nice week.